So this walkthrough is going to take us through a couple problems to talk about either growth or decay factor versus growth or decay rate. So these are the type of problems that you're going to see like on a state test or see on this unit test. And we kind of need to pull information out of this and use everything that we've learned to answer these questions. So let's look at this first example. It says in 1998, Clayton had a population of about 13,000 people. The population is increasing at a rate of 1.4% each year. Write a function that represents Clayton's population growth since 1998. Use your function to predict the population in 2020. Okay, so we know this is increasing at a rate of 1.4 each year. So the way this is set up and the way this is worded, it should tell us that this is an exponential function. So we are going to use this template, so this parent function. So in 1998, Clayton had a population of about 13,000 people. So that is our A. That is our starting population. Our starting amount is 13,000. The population is increasing at a rate of 1.4 each year. Okay, so remember that when we're given a percent, we cannot put that directly into the equation. So because we're increasing, we're going to take the 1.4% and we're going to add 100%. So that gives us 101.4%. Then we're going to change this to a decimal. So we want to go away from it being a percent. So this is 1.014 as a decimal. So this is our rate. This is, in the green, is our factor. So our growth factor is 1.014. Remember that this 1 right here tells us we want 100% of everyone that was there plus this little bit of growth. So we don't just want the growth. If you just typed in 13,000 times the growth, which is 1.4 or 0.14 as a decimal, if you type that in and you did 13,000 times 0 or 0.014, then that's going to give you 182. Well, I'm not going to go from 13,000 people down to 182. That's not even a growth. So if you get a smaller number, but it's saying you're growing, that probably means you forgot to add that 100%. So our growth factor is our rate plus 100%. So that means our growth rate, though, is still just the 1.4%. That's the rate that it's growing. Okay, so let's write this exponential function. So I know I'm going to use this template. So I have y equals our starting amount, which is 13,000, our growth factor, which is 1.014 to the x, because I want to put in any amount of years to figure out my population. So this says, what's the population in 2020? So I'm not going to use 2020. I'm not going to use 2020 as my x value because this is since 1998. So 1998 to 2020, that's 22 years. So my x is actually 22 years of growing. So when I put 22 in for this x, and I put that into my calculator, I get a population of 17,651.36. So we can say it's about 17,651 people. Okay, so let's look at example 2. In 2010, a city in Ohio had a population of 102,000 people. The population is decreasing, so that's important to know. It's decreasing at a rate of 1.2 each year. Write a function that represents the city's population decline since 2010. Use your function to predict the population in 2025. Okay, so just like we did the one before, we know this is exponential. AB to the x is the parent function that we're going to use. But now we're decreasing. So instead of adding 100, I want to take my rate away from 100. I don't want 100% of the population, so I need to take some away from it. So I'm going to do 100% of my population minus this 1.2%. And that's going to give me 98.8%. So I take that and make that a decimal. So it's 0.988. Remember, if it's a decrease, we should have it be less than 1 because we don't want 100% of the population. We want less than 100% of the population. So this is actually our growth factor. So 0.988, and our growth rate was the 1.2%. I'm sorry, our decay rate was the 1.2%. And just to fill in, our starting amount was 102,000. So let's write our function. Our starting amount was 102,000. Our rate, our decay factor, is 0.988 to the x. So I want to know the population in 2025. Well, I know that our starting point, our 102,000, is in 2010. So from 2010 to 2025, that's going to be an x value of 15. So we're talking about 15 years of decay here. So if I put 15 in for this x, I should get right around 85,104.86, which is about 85,105 people. Okay, last one. Since 1980, the number of gallons of milk a person has drank has decreased by 4.1. We're just going to assume, for the sake of this walkthrough, that it's decreasing by 4.1%, let's say each year. So go ahead and write that on your paper. In 1980, each person drank 16.5 gallons of whole milk per year. So that seems like it's our starting amount. Write a function to model the gallons of whole milk drunk per person. Use your function to predict the number of gallons of milk each person drank in 2005. Okay, so our starting amount is 16.5 gallons. We know it's exponential, so we're going to use AB to the x. This is decaying by 4.1%. So because it's decaying, I don't want that full 100%. I don't want all of the 16.5. I need to take away 4.1%. So when I subtract 4.1%, it leaves me with 95.9%. We want to move that into a decimal. So it's 0.959. So that becomes our decay factor, where our decay rate was the 4.1%. So our exponential function is y equals, what is our starting amount? 16.5. What is our factor? 0.959, and we want to keep it to the x. So this is, what are the number of gallons of milk drank in 2005? Well, if you remember, this is talking about since 1980. So that's 25 years we're talking about of this data. So my x is going to be 25 years. So you want to plug 25 in for x. And when you do that, you get right around 5.79 gallons of milk. So if any of that was like a blur, if you don't understand any of it, maybe you understood a couple of the problems but not one of them, just go back and re-listen to that problem and see if it makes sense the second time around. If you feel like you finished this and you still kind of have no idea, maybe go back through and put little stars next to what part you're having a problem with, and then let's talk about it. So maybe you fully understand like A's, like you understand your starting amount, but let's say you don't understand the decay factor. So let's put a little question mark next to that, and then let's talk about those parts where you're having problems. Okay, I'll see you in class.